So wonderful.
All right. Welcome to our session of discussions on Plato's Timaeus. And here we have a real treat for you. We have Michal, how do you pronounce your last name?
Paszkiewicz, Michal Paszkiewicz.
Paszkiewicz. Great. And
Yep.
Go ahead, please take it away.
Okay, so today's talk is where does Timaeus fit in astronomy? So I'm thinking of trying to explain to you a bit of a background where of where the history of astronomy was before Timaeus, what a bit of discussion about what is in the Timaeus, and then a bit about the influence on the future astronomy from Timaeus till today's date. And just before I go into any more details, this is just about me. I've got a degree in theoretical physics and a diploma in science and religion. I've worked mostly in software, and I'm currently working in cartography and oceanography, but I'm definitely not a professional astronomer. So that's my excuse if I can't answer any of the questions. On some astronomy, so I'm not sure how much of an astronomical background you have. So here I've got a Starium. I don't know if all this can get apps on your phone that do something similar. And essentially here you can look at the stars, you can change the dates, you can change the time, and you can see what happens to the stars. And this is something incredible because people didn't have this for the majority of human history, and you can very quickly learn or get a feel for how the stars work in reality. And the model is very good. To get anything more detailed, you would need a very good telescope to actually find issues with this or find something new with the real stars. So anyway, so the first thing to note is there's this red line here. Now this line is called the ecliptic. And essentially what this means is this is the path along which the sun goes, and then also most of the planets. So you can also imagine this as the plane that goes through the Earth. That is actually the plane of the solar system. So we can see here, if we change the date, as we change the date, the various planets move along this line, and the moon as well. So that's what the ecliptic is. Now the next thing to note is we can get an equatorial grid. So this shows the equatorial grid is a grid that is based on the North Pole up here, Polaris, and then it goes down to the south. And this is like the lines on a globe. So the meridian, the latitude lines, and so on. And the equator would be this line, except it's not aligned with our planet. It's aligned with the pole star. And so obviously what that means is that the Earth spins around like this, and we note that it's not in line exactly with the ecliptic. And here's the fun thing. The next thing is we can start changing months, and we can actually notice that over time the angle between our lines, our longitudinal lines, change with regards to the ecliptic in terms of angle. So this is essentially what is happening with the seasons. The higher up the sun goes, so the greater the angle between the equator and the ecliptic. That means the more we have heat and so on, because the sun's higher in the sky. And the last thing to note, I think, before we move on, is just we can change the years. And you will note that as we change the years, one second, maybe it's better to do this with the landscape. So if we zoom in, we can note that the stars in the background, they change slightly, and they come back every 4 years. And can you guess where that is? That's the leap years that come in. So essentially, this is the difference between the different rotations of sidereal year and the other years. So essentially, that because an actual sidereal years is actually 365 days and a quarter, you get this additional period of which the stars are moving around. and we correct this every 4 years with a leap day. So that's what this is about. That's a bit of a background into astronomy. We can always explore some more of this if you have any more questions. But it's good to get one of these apps and try this out, because you'll learn a lot just from fiddling around with the date and just looking at the stars. So that's really, really worth looking at. If you have a Mac, I think Celestial is the best app alternative to Stellarium. Anyway, back to here. So what happened before Plato and the Timaeus? And actually, there wasn't very much in terms of the history of astronomy. And we have a long period of astrology, starting possibly with Zoroaster or in some other person in Mesopotamia. But certainly we know that Zoroaster was an astrologer, but we don't really know when his date was. I'm using Riccioli's date, which is 1990 BC. It could have been earlier or later, we can't be sure. But astrology plays a major part in the story of astronomy. And for the majority of the history of humanity, astrology was almost the same thing as astronomy. People studied astronomy and they imagined it had interactions with the real world down here on Earth, that stars actually played an important part in our lives. And this makes sense because the astrologers would study the stars and they could predict when to do a harvest, when things would get cold. And it seemed like there was this very clear connection between the stars and what happened on Earth. Of course, now we know differently, but this came a lot later through a variety of things, through the rejection of astrology by the church in the 1500s, 1600s, and then through the Renaissance period with growth of enlightenment and a harder mathematical science. After Zoroaster, we have a variety of small improvements, but not much we know much detail about. Certainly mathematics, we know more about the Babylonians improved mathematics, especially incredibly, the Indians developed astronomy and mathematics as well. But we get to Thales of Miletus in 500 BC, who was the first to predict the solar eclipse out of the Greeks, and he measured the angle of the sun as 0.5 degrees. So this is quite an impressive feat as he started actually to take real measurements, and it wasn't just qualitative measurements as it would have been done before. We have Anaximander, Pythagoras. We'll go into a bit more detail in a moment. And then Pythagoras, of course, came up with talked a lot about solid spheres, about numerology and harmony of the spheres, which was had a huge influence on astronomy for a very long time. Cleostratus, who introduced the zodiac, and Enopides, who measured the obliquity. So the obliquity is the angle between the ecliptic and the equatorial, the equator of the rotation of the equator of the Earth, essentially, and the first measurement of the Greek. Yes, we'll go a bit more into detail on these in a moment. So let's start with Anaximander. This was the first cosmology that started to explain well what might be happening with the stars, and what we have is that Anaximander was the first to recognize that there wasn't obliquity at all. People weren't so aware of the various angles of the fact that there's an ecliptic that's a straight line that things are traveling through. And this was quite complicated because people, for example, didn't realize for a long time that the morning star was the same as the evening star, that it was just the planet Venus. And a lot of these other details were not so clear to people who weren't observing things day in, day out. So Anaximander was possibly the closest thing we have in the history of astronomy to an actual scholarly flat earther. We don't actually have much of a history of flat earth theory at all anywhere. But he didn't actually believe in a flat earth, he believed in a cylindrical earth, and that we actually inhabited the end of the cylinder, which was essentially flat. So that's why I say it's the closest to being a flat earther, because everyone else had spherical models essentially after this. But he certainly believed in a flat earth on the end of the cylinder, and that we had these rings, and that the shine was shining through up to the cylinders, all the rings. Oh gosh, here we go. And essentially what was going on is there were these rings or spheres of fire, and there were holes in them, which is where the light was shining through. And interestingly, you can see that the ordering of his his rings or spheres are quite unusual. The stars are on the inside, the moon is further out, and the sun's quite far on the outside. So this is entirely the opposite of what anyone could possibly expect, especially considering the advances been made since then. He also believed in the plurality of worlds, so that there were more worlds possibly inhabited or so on. We don't know much about. I don't think he believed in aliens, but certainly that our Earth was not unique. Next, we have Pythagoras. Of course, we talked about Pythagoras a lot in music theory. He came up with a lot of these theories of harmonies, but harmonies are not just the music, they're also in the spheres. So the concept of the harmony of the spheres is a very interesting one. It's about beauty of astronomical theory, and it's something that plays a major part in science since, I would say, and we'll get to that later. But certainly Pythagoras believed in this harmony of the spheres, a sort of mathematical beauty in it. So he was also a numerologist, which will also play an important part later on. But he certainly believed in a spherical Earth, and he studied regular solids, which is also something we'll come back to. But certainly these are all things to remember. Next, Cleostratus introduced the Zodiac. So that you might know there's 12 Zodiac constellations, and they are the constellations of the Zodiac are just the constellations that are along the ecliptic. So there are other constellations, but they're not along the ecliptic, so they're not part of the Zodiac. And that's essentially what that is. And the sky can be said to be divided into the 12 constellations. And this is what astrologers used for a long time for their predictions. They could say which part of the sky various planets were in, and they use this for their predictions and so on. That's okay. You're sad. Okay. Enopides was the next great one. So he was the first Greek to take an accurate measurement of obliquity, so the angle between the ecliptic and our equator, and he measured it as 24 degrees. So this is actually the maximum obliquity. So because the obliquity changes, you measure the maximum one, and that's actually the most of most interest to astronomers to understand what's actually going on. And he was the first he took the first measurement of the great year. So the great year is the amount of time that it takes for integer years, to be equal to a number of integer months. So 59 years can be counted in integer months, lunar months. But obviously it's not quite right. It's a bit off by here and there, but that was the first measurement of this kind. Next, we have Plato. So I've included in this section a few other people that lived around Plato's time. So these are people Plato might have known. Maybe they didn't exist, but maybe they did. And but certainly they influenced him, or he influenced them, and this formed a huge basis of the following millennia of astronomy. First of all, is Democritus. I won't talk about him too much, but he was an atomist. He believed in the plurality of worlds, and we know from Diogenes Laertius that Plato actually hated him. He wanted to burn his books, and he didn't like his theories much at all, which is interesting. A lot of modern scientists would trace their lineage back to Democritus, partly because of his view of atomism, which is more aligned to the atomic theories of modern and contemporary times. Philolaus is an interesting one. He believed in a central fire, possibly something like the first heliocentric theory. Then we have Timaeus and Plato, Eudoxus, who was a student of Plato, and Aristotle, who I think has to be included in this section, as his expansion of Platonic theory was pretty vital to what happened there. So Philolaus believed in a central fire. So actually in his theory, it wasn't quite heliocentric. Where's the other door gone? I don't know. So he believed in a central fire, but it wasn't the sun. Essentially, the Earth was had this central fire behind it, and it orbited around it. There was a counter Earth on the other side of the central fire, and there were 10 divine bodies. And this is why he needed his counter Earth, because he included the planets, he included the sun, the moon, the Earth, his central fire, and then he needed one more item to make it to the magical Pythagorean 10. So he devised this idea of the counter Earth, which would balance out the universe. The central fire was something that was behind the Earth. I guess in some ways you could say it explained things like volcanoes, but we can't be quite sure why he came up with this. But certainly the medieval astronomers would refer to Philolaus as their greatest ancestor who came up with heliocentric theories. So Timaeus is the next one. These are two I've attached to a translation of my own from Riccioli's New Almagest, and some theories on who Timaeus is really. We don't have any sources really about him that don't come from Plato, but certainly it's interesting that that we do have accounts that disagree on whether Plato had bought books from Philolaus or of Philolaus for either 40 or 100 minae, and that's interesting. But there's a theory that he may have used those books for writing up the dialogue of Timaeus, and there's the alternative theory that Timaeus was a real person, and that Plato copied a lot of his works and what he said into this dialogue. Personally, I'm of the opinion that it's probably quite likely to be a similar case as with Socrates, that he was probably a real person. He may not have said what Plato wrote that he said. Maybe Plato was assigning to him things that he believed himself, as is likely he did with Socrates. Also to note, there was a pseudo Timaeus who wrote the Natura Mundi, and actually we can modern philology has shown that it's most likely a 1st century BC writing. It's probably not by any contemporary of Plato. You can sleep with me, it's okay. That's okay. That's okay. He'll be okay. Anyway, moving on. Plato's cosmology is probably best described actually by Eudoxus, who was a student of Archytas and Plato. And the reason for that is Eudoxus actually wrote down a model that had a few numerical values that actually had a description of how it looked. He was a student of Plato, and it matches quite well with what Plato wrote down. And you can see here, this is the kind of model he had. There were these spheres, they were attached to different points, and they rotated in different ways. And actually, the retrograde motion of planets could be described in this way. So there were a variety of spheres needed for description of different things. The moon needed 3, the sun needed 3, the planets used 4 each, and then the stars used. So, okay. So looking into what's actually in the Timaeus, I can't quite see because of the thing there. Okay. So, so first of all, we have these 2 quotes here. I think it's interesting that that the first quote actually suggests that Plato had a belief in astrology. He clearly links the arrangement of heavenly bodies with convulsions of nature. So most likely with earthquakes, with floods, and fires. And that's quite interesting to note, of course, because he doesn't explicitly provide any astrological predictions or theories within the Timaeus, as far as I can see. And but certainly that he sees this link, and certainly this would have been the case. People would have believed in these things. They would have believed in the signs in the sky, and it's certainly that way. It was certainly that way for a very long time. And the other part is his belief in a creator, and it's not just any creator. He clearly believed in a sense of cause, and that there was a first cause, and it mirrors quite well sort of Christian belief of a creator God. This will. Okay. So the other thing that comes into the creator God theory is this thought of unchangingness of this immutability. So the sort of perfection and immutability of God was to be reflected in the nature of the world, because it reflects the God that created it. And this is something that played an important part in astronomy for many years. The heavens are seen to be a perfect creation, and therefore they must follow strict rules, and they wouldn't deviate from them. So here we go. We have this quote: "Why does the Creator make the world? He decided that all things should be like himself. So he set it in order, which was in disorder otherwise. He'd framed the universe to be the best and fairest work." And the other part is belief in plurality of worlds. There's no belief in plurality of worlds in Plato. He believed that if there were more than one world, then actually they would consist of another world, which was just one world. So it didn't make sense for him to call multiple worlds a world. There you go. We have the elements. Now, the elements don't play quite so much a role in astronomy in Plato's time. He certainly derives the cosmology of the Earth from the ratios of fire, air, earth, water, and so on. But I think this doesn't really play so much a role in Plato as it does later on in Aristotle. And we'll come to that in a moment. And here's another part. All that he did was done rationally in and by himself. So, and circle turning within himself, which is the most intellectual of motions. So here again, we see this perfection of the circle and his belief in a rational universe that made perfect sense and was perfect in this mathematical way. This one is quite important. So I find this one interesting. This one, I think, so he talks about this letter X style shape of circles, and this matches the theory we have from Eudoxus in more detail. It's this idea of having multiple spheres that are at different axes, and this explains why there is an ecliptic that is at an angle with our equator. It's in this X shape, and I think in another translation I had, they started as two rings that were in the same plane, and then God rotated them out, and that was a bit interesting. But I guess he was trying to explain how these things move, and certainly the Earth does move, and the obliquity does change. So we have that. So we talk about 5 wanderers. Of course, we've got to remember that at the time there were only 5 known planets. So you had Mercury, Venus, Mars, Jupiter, and Saturn, and the others had not been discovered at that point. So that's worth to note. And by Plato's time already, it had been discovered that the evening and morning star were one and the same, and that they were Venus. So that's good to take note about Plato. And this is another one, again, about the circle. The gods were made in the form of a circle, which is the most perfect figure in the figure of the universe. So these are really important because you do have a spot on you, that's right. You've got chicken pox. So the circle was considered this perfect thing, and this is something that was maintained for a long time and was a reason why astronomers struggled to leave the Ptolemaic system later on. So so Aristotle came after Plato, and he increased the amount of spheres to 56 spheres. Now, that's an incredible amount of spheres. Under Ptolemy, this actually decreased, and he also invented the ether. So the ether was an additional element, so that the stars were not seen to be any of the four elements of the Earth. They was an additional element. It was the most perfect element, and it couldn't be affected by the other elements. Heavenly bodies were the most perfect substances, and he also believed in hylomorphism. This theory is that there was matter and form in all objects, and for the stars, the ether was the matter, and uniform rotation in a circle was the form. So this perfect rotation. He also believed in telos. So this is the concept that everything has a direction or a natural state it wants to tend towards. And this was applied to the elements. And this meant that, but essentially the theory was fire wants to go upwards. What goes even further upwards was the ether. And earth wanted to go downwards, and water would go above the earth. But this was an important part of the theory that had a huge effect on the future, because this meant that everything was related to the center of Earth as the center of the universe. And this is something that was very hard to get rid of, because if this was the theory as to how the elements worked, then everything was related to the Earth, and actually disengaging from the Earth as a center would actually overturn the entire physical theory of Aristotle. So after that, we'll go through a few scientists. I've picked these just to try to pick out scientists who are related to the theories of Pythagoras, Plato, Aristotle, and we can see how these concepts that we have talked about changed over time. The concepts of the harmony of spheres, the concept of perfect circles, the concept of Earth as at the center. So Ptolemy was the next great astronomer, really, after Plato. He wrote the Almagest in 150 AD, and he created the system of epicycles and deferents. So a deferent was essentially a circle that was that went around a point that wasn't the center of the Earth, but he created the equant point. So you would have that point there, and from that point, the planets and various motions were actually still a constant speed, angular speed, and therefore he could still claim that it had this perfect motion according to Pythagorean theorem, and he could keep to the concepts of perfectness, of immutability, and so on, which was clearly very important to him. And Ptolemy's theory lasted for about a millennium and a half before anything else started happening to astronomy that was of any note, to be honest. I think there was more progress in Indian astronomy. Certainly, the Indian astronomers came up with the Tychonic model before we did in Europe, but they stalled around there, and they didn't make further progress from that. So I'll only cover European progress in astronomy through that section. So Copernicus was the next real overhauler of Ptolemaic theory. He switched to a heliocentric system with the sun at the center, and actually, contrary to popular belief, he didn't get rid of the epicycles. He still had 34 spheres, and which in his Commentariolus, which was published by Rheticus in 1516, I think 1515, and growing to 40 when he published the Revolutionibus. So he actually had a similar amount of spheres as Ptolemy required to explain his theory. But certainly the theory had a much stronger explanation for how retrograde motion of planets worked. He still used perfect circles with a deferent, and so the models you see in pictures like this are never actually quite accurate. There would have been multiple epicycles. They would have been off center slightly from the center of the sun, from the center of the Earth, and so on. And however, the spheres still had a constant angular velocity in the circles, and this still continued to be so for a while. Tycho essentially reorganized the model of Copernicus. He put the Earth back at the center, but then the planets went around the sun. And essentially, mathematically, the Tychonic system is exactly the same as the Copernican system, just taken from a relative point of the Earth. So mathematically the same. It's just the position from which it's observed and what's taken as the actual center of the universe. And still, you still have the same fact that all the motion is still at the same angular speed and so on. Now, Galileo, I'm only going to talk a brief bit about Galileo. We could talk a lot about other bits, but his publication of Sidereus Nuncius was probably the most interesting for change in attitudes from Platonic astronomy. And the reason for that is he discovered the Galilean moons. So they are the moons that are around Jupiter. And this was the first discovery of something orbiting a planet. And certainly it's suggested that the Aristotelian telos theory of elements going towards the Earth couldn't be explained so well anymore by this, because why on earth were they orbiting Jupiter? Actually, that's one possibility. And the other possibility that was believed in is that this actually explained that epicycles were true. This was clear evidence that objects moved around a center that was not the center of the Earth or center of the sun, that things could actually move around points that were in orbit around the Earth or the sun. Now let's go there. Kepler. So Kepler's a very interesting subject. So first of all, he publishes Harmonicus Mundi in 1619, and this was largely about the harmony of the spheres. And what's particularly interesting, I think I've got a second one. Okay. Is he very clearly linked to Pythagorean and Platonic theory in his work. He wanted to show, he had a really strong belief in mathematical beauty, but he had a different perception of what that would mean. He brought in elliptical orbits. Now, a thing I always find interesting about elliptical orbits is actually you can describe any ellipse with epicycles, but certainly what ellipses are is they are a subset of epicycles. So you might be able to describe all ellipses by epicycles, but you certainly can't describe all epicycles by ellipses. And this was a constraint on scientific theory, so I think it's certainly a huge achievement. Regular solids, he tried to fit regular solids between different planetary orbits, and he also, I'll go back to that actually a bit later, but this is clearly a link back to Pythagorean theory. Angular speed of the stars was no longer constant. So instead of angular speed, what we now have is we have the Kepler's laws, and the second of Kepler's laws tells us that the arc going from the locus to the actual object sweeps out an equal area in equal time. So as you can see here, especially in this diagram, is as the object gets closer, it actually goes much faster, and the reason for that is that this radius length is smaller, so therefore it needs to go further along in terms of angular distance to cover the same amount of area. And let's go to the next section. So Kepler finds that the ratio between the Earth's angular speed as measured from the sun varies from the ratio from 16 to 15. He actually equates this to the semitone ratio of mi to fa. And he then says that the Earth sings mi fa mi, so we can gather ever from this that misery and famine reign in our habitats. Now, I think this is a very interesting excerpt from that. He's clearly directly linked into Pythagorean and Platonic theories of music. And he also clearly links this to other things just from the letters. And it's a very, I would say, this very medieval approach to science, where everything seemed interconnected, where it's almost in a way in astrology, but even further, that he makes direct connections between different sciences, regardless of how he does it, and which is particularly interesting because he was a very strong believer in mathematical beauty, and he actually often rejected other theories. For example, he strongly rejected Hermetic theory, which was quite popular at the time, because he didn't believe it was mathematical enough. Riccioli, I mentioned Riccioli. I'm actually working on translating some of his work, so I find it very interesting. He believed in a geocentric theory. It was a bit like the Tycho's theory, but he actually reorganized Kepler's theory so that he used elliptical orbits, but he put the Earth at the center. And the reason I say this is because I find this interesting from the fact that the concepts of mathematical beauty and immutability of the stars has changed here on the other side of the heliogeocentric argument. So he argues for geocentrism, but he has already accepted Kepler's abandonment of perfect circular orbits, and therefore we see that both sides are now moving away from the more typical Pythagorean or Platonic theory of beauty of the stars, and they are accepting this new mathematical formulation, which is elliptic. But in a way, it still retains mathematical beauty. It's just a change in what that actually means. Newton was, of course, next huge movement. His theory of gravity made a huge change to destroy the old Aristotelian theory of telos of the elements. Now, instead of the elements playing the major part in, and this link to Earth's center being the major part of cosmology of the universe, we have a force that behaves between every object that has any matter and weight. And he provided clear laws of motion that gave us a very mathematical understanding of how different objects interact, both locally and in a wider solar system and universe. And sure things were moving slowly in that direction already. The likes of Galileo and Riccioli had made huge progress in local mechanics, and this was surely coming eventually, one or the other. But certainly this represents another step in abandonment of Platonic and Aristotelian fundamentals in astronomy. Edmund Halley published in 1718 a paper that showed movement between stars relative to each other, and this was really the final straw in destroying the idea of a perfect and immutable outer sphere of stars. If the stars could move relative to each other, then they were no longer fully immutable and perfect and unchanging, unmoving. And Lagrange, by the time of Lagrange, we had a very mature planetary theory. I've kind of included him. I don't know if you've been paying attention to some of the news, but James Webb Space Telescope is using Lagrange's theory to find a Lagrange point, which is a point distant from the Earth, but that is a stable position where an object can be in the orbit of the Earth and not require much fuel to keep it stable in that place while moving around the sun. So that's this is from 1774, and it still dominates the physics required in rocket science today. Einstein is someone we definitely need to talk about, once again, because of his relation to the concept of mathematical beauty. And I think this is the main thing that's left from Pythagorean and Platonic theory, is that a lot of scientists, especially astronomers, believe that there needs to be a mathematical beauty in their theory, and that this is what they actually strive for in the development of the theory. And certainly general relativity is incredibly mathematical. It's very difficult, but it also has a certain beauty to it. And the fact you can change coordinates very easily, the fact that it has this geometrical shape to it, that it's a geometrical theory, is very beautiful. According to Einstein, of course, he struggled with the ugliness of quantum mechanics, but in a way that's quite interesting as well. And that's quantum mechanics is also has some strains of thought that can be linked back to Pythagoreanism. For example, the numerology of having quanta, that there's different modes depending on numbers that are integers coming into the theory. So I certainly find that interesting. But there was always a debate about the beauty of the theory, and this has continued up to this day. I mentioned string theory, but it's essentially all modern theories. People are looking for a theory of everything, and one of the main factors these days is people look for something that's beautiful. So this is something that's particularly true in string theory and supersymmetry in M theory and so on, where they might not be able to make new predictions or actually experimentally verify that their theory is better than anything else, but that scientists will try to argue that because their theory is beautiful, because it has symmetry, therefore it should be the adopted theory. And I think this is a very clear link to the concept of harmonies of the spheres, especially in string theory and M theory, where actually the strings or membranes are rotating in integer modes that are very, very much clearly related to the Pythagorean numerology. So I think that's it. That's all I had to say today. If you have any questions, I will try to answer them, but I can't promise you anything. So thank you very much.
That was fantastic, Michal. It was the scope was large, but you really followed those themes. So it was really fantastic. I have dozens of questions written down. Yeah. But maybe I'll start with some of the, because I'm not somebody who's read a lot or thought too much about astronomy. It's always been interesting to me, but it's always been a sort of amateurish, unstudied thing. So I'm going to ask, if you don't mind, some like super basic questions just to understand. So one of them is, can you explain to me observationally what does the retrograde motion of the planets mean? Like if I were to, what does that look like observationally for somebody?
So this is great. We can use Galileo for this. So a really good one to follow is Venus, for example, and we can watch this. So Venus travels along with the sun. You see this? I don't know how well you can see my screen.
I can see it quite well. Yeah.
So essentially, Venus keeps going one way, and then what happens eventually, as you keep going this way, what happens? It starts actually eventually coming back the other way relative to the sun, and we'll get there eventually. We probably need to follow the sun slightly.
So is that's showing? Can I just to understand what we're seeing? We're seeing the daytime path of the sun and the nighttime path of Venus, or is this the same time?
So what's happening is I'm scrolling through the days. So every time I click this, that's an additional day later.
Oh, so this is like the noon position, or what the position at what time?
This is at 11 p.m. It doesn't really matter.
Okay, at 11 p.m. that's the position. Yeah. If you were to look at it every day, that would be the relative position of the sun and Venus.
Yeah. So
okay, got it.
So the important part is what happens to Venus and Mercury, say, relative to the sun, and they keep going in one direction, and then look what's happening here. Mercury starts going back the other way, and the reason for that is, of course, is that Mercury is orbiting the sun, right? So
right, okay,
then in the other direction, and okay, this is quite obvious with Mercury and Venus, but then much less obvious when it happens to Mars, because it does happen to Mars. Look what's happening with Mars. He's going back the other way.
Yeah. Okay.
And so essentially that's the problem. And this happens due to the fact that we are orbiting the sun, and therefore we are at one point moving away from Mars, and at one point we're moving towards Mars.
Yeah.
When you're moving towards Mars, he starts zooming past you, right?
Right.
As opposed to actually going in the direction he's actually traveling.
Okay. Yeah, that makes sense. And the visual, yeah. Okay, that's very cool.
Cool. What are the other dozen?
So I have a question about the ecliptic. So there's like so is the fact that there's an ecliptic is a result of like if we look at in our model, right, in the solar system, that the orbits around the sun are kind of on the same plane, right? Is that why?
Yes, exactly. Yeah. So that's exactly the fact. They're in a plane, but the Earth, while it's in a plane, spins at an angle to that plane. So it's spinning here at this angle while the Earth is in the plane.
And why is it that all these objects are in that plane? Like, isn't it conceivable that you could have satellites orbiting all sorts of ways around the sun?
Yes, and I mean certain various. I think Uranus, is it Uranus or Neptune? I can't remember. Is one that goes quite far out, but certainly you can see Castor. If we find one of the smaller dwarf planets, it's that some dwarf planets go really, really far away from the ecliptic, and you can have them, but the majority of the solar system is within the ecliptic, but certainly they don't have to be. And there's I'm not sure I'm the expert on solar formation. We'd have to ask someone more specific there, but there are many theories for why the solar system forms this way.
Okay. Okay. Should I just keep on asking these basic questions, Brian?
I'll answer what I can answer, of course.
Okay. So I was just curious because we were talking about flat Earth and cylindrical Earth and spherical Earth. Like, I'm just, it's gonna sound weird, but now people, the flat earthers, contemporary flat earthers, they have all these like common sense objections to the spherical Earth, right? They're like, oh, why don't people on the bottom fall off? Why does it feel flat? Like, were these concerns before? Like, how did people think about that in, like 2 millennia ago? Did they worry about these kind of common sense objections of just like, it not being obvious observationally that we're on a sphere?
Well, I think anyone interested in actual astronomy would have not been concerned with it, but I think for the general populace, they might have considered the concept of a spherical Earth quite ridiculous if they'd only experienced life on the plane or something like those ways. But certainly in a flat Earth theory, in fact, much of the current flat Earth establishment stems from 18th, 19th century American Protestant movements. They don't have any relation to archaic theories or studies at all. So certainly there's a common misconception that medievalists the medievals were flat earthers, but no, they might have been geocentrics, but they certainly weren't flat earthers. We don't have any evidence to believe such a thing.
Okay.
And most of the common sense objections can be refuted fairly easily. The problem, of course, is that to prove it ultimately to flat earthers, you either need to actually get them to stand out at night and watch the stars for a while, or take fairly slightly difficult measurements, or to believe in existing theories, and a lot of them will reject, for example, pictures from satellites or anything of the like. So the problem is actually getting someone to experience these things with you, and to take the time to actually study these things, and that can be hard, of course.
So that leads into, I had some questions about measurement. So I had two questions. One was I think you talked about Thales measured the angle of the sun, and I don't know what the angle of the sun is. And the second measurement question is, you mentioned, I think, I don't know who, Oenopides measured the obliquity. Like, what tools would he use to actually measure that? Like, how did people grid out and actually measure things in the sky at that time?
So from what I recall, Thales actually used the pyramids of Giza as a measurement tool, and he was using using the shadows of the pyramids to take various measurements of the sun. And he measured the sun to be 0.5 degree wide, and certainly.
Oh, I see. Okay, so that's like how big in the sky is the sun? That's what the angle of the sun means. Right. I see. Okay.
And that's fairly accurate. The sun is about 0.5 degree. The moon's about 0.5 degree, and that is because they're the same actual degree in the sky. That's why you get the actual eclipse.
Yeah.
But that does change slightly as well, depending on where they are in the sky. Sometimes the moon's a bit closer or further away, for example, so it's not always exactly the same. And certainly measurement tools for a long time were far more simplistic than we have them now. But measuring an angle can be as simple as having a very long stick with a little thing on the end, and then you can, for example, slide something up the stick and then try and actually look down the stick and see the angle along the stick, and then measure what that is. So it can be primitive, but these things eventually developed into tools like astrolabes or a variety of tools similar to astrolabes, and quadrants, sextants, and so on.
Okay, I think I have one more of these basic type questions, but I can just keep on going until, Brian, you interrupt me. But one question is, yeah, can you talk about the order of the spheres? Because like I guess like we see the Ptolemaic model, and you've got the moon kind of like third away, kind of like inverse of our model if you switch the sun the Earth for the moon. But like you talked about different ways that different people had ordered the spheres, and like what went into the understanding of the outside thing.
So the primary reason they could reverse the order of the objects in the sky was that we could start using parallax. The parallax is the concept of why you can, for example, close one eye, actually see something in different position, right? If I close one eye and then the other eye, my finger moves across the screen. Currently, with my left eye, it's to the right of the sun. If I switch eye, my finger's now to the left of the sun. So by taking measurements from multiple points, measuring the various planets against the stars, you can see a small parallax. And this was why you could tell that the planets were nearer, why the sun was nearer, why the moon was nearer. But then there was the problem of the stars. The stars were so far away, you couldn't measure the difference between them. And then, so therefore, for a very long time, the stars were considered to just be one sphere on the outside, also known as the eighth sphere, or later on it became known as the sphere of Sacrobosco, who wrote a lot about the eighth sphere.
Okay, okay, that's cool. I didn't know that. Should I keep on going? I guess the questions will be of a different type now. Maybe will require more exploration.
Okay.
Brian, do you have anything, or should I?
No, please
go ahead.
Go ahead.
Okay. So, okay, well, this one is maybe clarificatory as well. I was curious what you talked about Aristotle's 56 spheres. did you mean like movements, or did you mean like heavenly bodies, or what were the 56 spheres of Aristotle?
So Aristotle's theory was essentially it used the Platonic theory underneath. So this is a simple model of what Plato's theory was like, especially as it's described by Eudoxus. But this is actually simplified. We know that for the planets he used 4 motions, but these are the 3 that are required to explain the retrograde motion. And then there would have been one more sphere like this on the outside that would have been required to explain why those 3 spheres were going around the Earth. So that's the 4th sphere. Now, as you look in more and more into the details of planetary movements, you notice slight perturbations, slight changes, and then the way to deal with that in antiquity was you just add another sphere to explain the additional change that wasn't explained by your previous spheres. So when you're wrong, you add a sphere. That's essentially the premise. And the same happened when Ptolemy reordered his model. For a long time, various astronomers would explain change, new discoveries in planetary movements with new additional spheres. Does that make sense?
But are those spheres, are they associated with another heavenly body that's posited, or they're just no? Okay.
But
they're just movement patterns. They're like movement.
They're a mathematical tool used to explain motion, but certainly in some theories they would have considered them real objects that were actually they couldn't explain very well what they were, but they were real, and they actually,
there's just no visible part of, no specifically visible part of them. You just see their effects.
Exactly.
Okay. Okay. And then I was also curious, like, what? So is why Ptolemy had that deferent? That was also to help explain some of these motion things.
So actually, the deference is interesting because with the deference, so moving the center of the orbit away from the Earth. This is almost, you could say, the first step towards building an elliptical orbit, right? Because the ellipse requires a locus that's away from the center. The only difference is that here we still have a circle and not an ellipse, but actually, as I mentioned earlier, you can describe an ellipse with multiple epicycles, and the epicycles that were being built, they were essentially tending towards an ellipse, but not quite there.
So the motivation of it was basically to describe the things that look different from just a plain circular motion.
Yes, and one of the main factors actually there was that the planet did increase in size and brightness at various points in their orbit.
Yeah.
Obviously, size wasn't so noticeable until much later on when we had telescopes, but certainly brightness was clearly increasing and decreasing at various points in the orbit.
Okay, interesting.
And this could be explained by the deferent.
Okay. And I was also curious about the deferent because you mentioned sort of later in this story that Aristotle's kind of elemental theory and becoming a problem or a barrier. But it seems like here, still as soon as you get Ptolemy's model and the deference, then you have a problem with sort of saying that Earth things go to the center of the Earth. Don't you encounter the problem earlier, and what was that grappled with?
So the fact is, you had a deferent, but actually the center of the universe was still the Earth.
Okay.
So I think a lot of modern contemporary geocentrists do the same thing. They say, well, great, we have all of these theories, but actually the Earth's still at the center, and actually something will that add up magically, and it will still all rotate
Okay.
around the Earth, and it's essentially what was happening back then.
Yeah, okay, that makes sense. So the circular orbits don't need to be around the center of the universe. They can be off kilter, but the Earth needs still to be there.
And certainly when we these days, if we say the Earth goes around the sun, that's also not entirely true in Newtonian theory. Well, not now around the center of the sun for sure. In Newtonian theory, when two objects are moving around each other, they actually move around a common center of gravity or mass. And it just so happens that actually the sun is so heavy that this center of mass between any of the planets, even with Jupiter, it's still within the sun. So we are often orbiting around a point that's within the sun, but it's not actually at the center point of the sun.
Mm-hmm.
So the difference is actually something that is supported by Newtonian theory later on as well.
So also curious, in reading the Timaeus, so why is there motion, right? So like in our kind of, I guess in our kind of like Newtonian view, we have this gravity and the forces, and we think like that's a way to think about why there's motion and why it's circular or elliptical or whatever the case may be. And then in the Timaeus, you have the sense, why is there motion? It's a bit kind of inertial, kind of seems a bit like inertia, but it's also it's also animated. It's a soul, it's living, and so it's kind of got that motive power, and then it's shaped spherically. So you get the motion from it being animated and the circular direction from the spherical shape. But I'm kind of wondering what's the in between. Is there an in between? Like why? I don't know, pre-Newton. I don't know, like Kepler or Copernicus or some of these other people. How did they understand why? And even earlier, Aristotle, why did they? How did they understand why there is motion and why it is circular-ish?
Well, I think this is just they believed in this perfect universe, perfection of order. I guess it tied into I think most of those theories would have linked to a creator God putting them in motion at some point in that way, and that they matched him in perfection, and that they had to be these perfect spheres, and that's essentially pretty much it.
Mm-hmm.
I think even Newton said that why does it happen? Well, actually, the angels put everything in motion and keep them in that motion. So it's there wasn't much explanation for why things had got into that way or why they needed to be in that way.
Mm-hmm.
And these are problems that only started to be rediscussed in modern times, really much later than the Renaissance as well.
Mm-hmm.
And I think even now, planetary solar formation theory are still developing quite fast. There's still a lot of new theories, and I think it's only really maturing at this point right now, really, to be honest.
Mm-hmm. Okay, so that makes, I guess the part that I'm missing is the kind of understanding of what the motive force was, because like the circular thing I understand, like they thought there was something circular in shape for most of these people. I don't know about
Your
Kepler and Copernicus.
About, like the telos of the why are they going around all the time?
Is there something pushing them, or they just go unless they're stopped from going, or they're alive and going? What's keeping them going?
So I think that ties into this concept of the ether. Of the ether is that the ether wasn't affected by any sort of planet bodies on the Earth. It was different. It wasn't affected, so it didn't feel drag or anything like that like we feel. But I'm not sure I can answer you entirely there.
Okay.
I think there's a piece of the puzzle missing for sure.
Mm-hmm.
And maybe they didn't just ask this question to themselves.
Yeah. Is there a good sort of history of astronomy that you would recommend that would cover something similar to what you did here?
Well, I'm translating Riccioli's work, it's when I publish it, you're absolutely feel free to buy it. But it's not entirely in line with contemporary theory. There are different sides to various arguments. There's different dates that people now believe that are different, and I'll cover some of that in the book. But I'm not sure how far back various books go. I would probably recommend some books by Duhem, D-U-H-E-M. He covers a lot of history of astronomy, history of science. But I'm not sure about a particularly great book. I think most of the things I've read I've acquired through numerous sources rather than.
Maybe your preface or your introduction can give a sort of summary.
Yes, I've got a. One sec. So I've got a section on models. It's not entirely finished yet, but when I've got some drawings in here, I think this will cover most of the things I talk about and development.
Oh, great!
Over time. Unfortunately, it finishes about 1651, so I'll probably release books in about 10 years that will cover the period after that. So stay tuned. But otherwise, that'll be it.
Oh, the layout and the typesetting makes it look very, very finished.
Oh, thank you very much.
So I was curious too, like how did you come on this translation project? What's the history? Why did you decide to work on this? And
so I've been taking photos with a telescope of the moon. I was interested why the moon's craters were named in such a way. So Riccioli is the person who created the map of the moon and named the craters. And then it sort of tied into other interests I had. He covered the Galilean controversy. He came up with the theory of a Coriolis effect. So that's the effect that you have that, for example, bullets swerve to one side because of the spin of the Earth, and also why you have cyclones and anticyclones. And he predicted this, and he said, well, I can't measure it, so therefore the Earth can't possibly spin. And for hundreds of years after that, people couldn't measure it until pretty much Coriolis himself, who was an engineer working on cannons, and he spotted that he could measure it. So that's the point at which it could be measured. And so this work just intrigued me from a few different angles, especially because I've worked with weather systems in my current work. So yeah, there are multiple reasons I was intrigued by it.
And had you been a Latinist prior, or did you?
I'm learning on the job.
Okay, wow, that's very impressive. Yeah, and did was his name Coriolis? Did he make the connection with the prediction, or who sort of?
So I don't think he was Riccioli at all. He literally spotted the effect, and then he theorized why it could be, and he pretty much figured out
the same reasoning.
But I think the much stronger theories are with weather theory later on. I think that the effects on weather patterns in the creation of cyclones are just undeniably true. It's incredible, in fact, how well we can predict how cyclones behave, and just based on this one, the Coriolis effect, which is the resultant of the spin of the Earth mixed with the pressure gradient. So when you get a pressure change, and then together with the Coriolis effect, that's how you get your cyclone.
Okay, we're running down my questions. We're getting there.
Okay.
Well, so one smaller. You mentioned some. I just missed it. You mentioned something that in Indian astronomy they had one sort of point of progress before the European tradition. I missed what that was.
So that was Nilakantha Somayaji, and he published a model that's pretty much the Tychonic system. And this was about...
Oh, the Tychonic system. Okay, yeah, that was the word I missed. I see, okay.
Pretty much the same thing, except he published it a while earlier. And actually he was fairly influential in Indian astronomy. But yeah, certainly they didn't make much progress from there. And I think we see that in Indian and Oriental astronomy from that point onwards was largely dominated by Jesuit missionaries who brought over European astronomy to the East.
Okay, interesting. And yeah, I was wondering about Tycho and Copernicus and that sort of era. Like you mentioned Kepler kind of had this very Platonic resonance, and he talked about music in the same kind of breath. And is that sort of worldview apparent in the near contemporaries, or people closer, like people like Tycho and Copernicus? Were they making, did they think of it, I don't know, things in that sort of holistic?
I don't think anyone else really followed Kepler's style. In fact, personally, having read Kepler, I find it almost unreadable. It's very difficult to follow. You need an incredible grounding in music, especially music of that time, of science, astronomy of that time, and then how it all links together in his crazy theories, linking all the regular solids in as well. There's a lot of theory. It's a beautiful mathematical theory, but certainly I would say it doesn't really hold water. And the main thing that remains from mathematical beauty in contemporary theory is just concepts of what, the concept that it should be beautiful, but what people believe is beautiful in mathematics has certainly changed. And in modern times, often that's just symmetries, which is in a way a symbol of laziness of mathematicians, because if you get a symmetry, you can actually solve equations a lot easier. You solve it once and you can almost multiply it through the symmetries and have your results nicely and easily.
Okay. Yeah, that's interesting. I'm curious to read Kepler now and probably not make much sense of him also.
Yeah, I haven't found a very good translation either, which probably doesn't help.
I was curious to get into, I don't know, just your thoughts on, like, you were talking about Einstein and quantum mechanics and the aesthetics over there. I mean, I'm wondering if, like, do you have that same impression that there's something ugly about quantum mechanics? I don't know. I've seen, like, I don't know, Feynman's presentation in quantum electrodynamics, like he makes it seem very, I don't know. It doesn't seem so ugly. It seems very, he almost makes it seem like intuitive almost. I mean, there's like the determinism randomness problem, but that seems to be maybe
that's
maybe an epistemic problem, or may not be a. I'm just curious on your thoughts on that. Do you share that?
Well, I think the randomness is certainly one of the biggest problems in terms of making it an ugly theory, because something that was considered beautiful by Plato or Pythagoras was this actual thing about order. And you don't have order if you have random effects. You only have order if you can predict what's going to happen. But it really, whether it's beautiful or not, is really in the eye of the beholder. Say at this point in terms of mathematical theory, and certainly the quantum mechanics opens up a variety of questions in philosophy as to what it means, and how to interact with this, because you no longer have the strong determinism of Newtonian theory. You have this new randomness that can be hardly be explained, and you have some theories that always with chaos you can get some theories as to how behavior looks like on a larger scale, but you try and go into the details, you can no longer do that.
It's striking how mathematical though, like it's still, you can still, I mean, maybe you can't predict, you can't say specific, make very specifically, but it patterns math, everything still patterns mathematically. That's still kind of a striking, if you kind of have this idea that the cosmos is mathematically ordered, it's maybe a different kind of mathematics than you're used to using, but it's kind of, that's also kind of striking, that this realm of mathematics, probabilities and things like that we, or types of, areas of mathematics that we didn't know really mattered at that level. It's like, actually, we've developed the mathematical tools to describe this. Like, that's still kind of striking.
And I mean, I think we're definitely leaving astronomy here, but it's certainly an interesting philosophical question.
It's a Platonic question.
Why can we explain things with mathematics? Why is the universe rational to some extent? Why are we able to understand it? And that's been covered through many people in very many different books. And I'm not sure I can summarize it in a sentence or a paragraph or a book even.
It's like you said, it's like a subjective thing. I guess I'm saying, like, I find something disturbing about quantum mechanics too. The determinism, randomness kind of thing a little bit, but there's much that it's kind of fills me with awe and wonder as well.
For sure. But
it's interesting too. You brought up the quanta, and that kind of, like, I don't know, it's sort of like atomism of a different sort, right? A kind of return to atomism in a way of these sort of fundamental, I don't know, like the Timaeus triangles. There's this I don't know.
But I think the part of the problem with beauty of quantum mechanics is that a lot of physicists will want to link that in with other theories, and I think most physicists would agree, for example, that quantum chromodynamics is more beautiful than quantum mechanics by itself. As soon as you can start explaining how the quantum forces start reacting or just changing to the other forces, how they relate to each other, then you can start having a theory of everything, and then that's what they consider more beautiful. And this chase for a theory of everything is essentially something that does them from this concept that everything should be rational, should be beautiful, and should be possible to explain on the back of a t-shirt. Anyway, any more?
I have two more.
Okay.
Have I exhausted you?
And I can go to bed.
Okay. I was just curious. I don't know what you think of modern astrology as it is today. I don't know, just thoughts on the astronomy they use, the kind of reasoning they use. Just, I don't know.
I'm not sure I can comment. I haven't ever consulted a modern astrologer. I know a bit about astrology, but only medieval astrology. They use these funny square shapes, and actually the only reason I know about it is because it's useful for figuring out what various astronomers use for as their model for predictions, or knowing where stars were at a certain time, and then them seeing how accurate they were. So it's useful from an astronomer's perspective to see what people were doing and how accurate they were. But I can't comment on contemporary astrology at all. My personal opinion is it's a lot of tosh, but you are welcome to your own opinion, I guess.
Yeah. Okay. And then my last question, I was just curious, we're like approaching the spring equinox, and in the Persianate world, much of the Islamic world, it's a big deal. It's something that, especially a lot of the Islamic astronomers were Persian themselves. And so, sometimes, not just pure astronomers, but theologians and metaphysicians. And there's all sorts of like theories and thoughts on the spring equinox and its significance. I'm just curious if you have, if it's something that, these kind of the dates and these kind of points in the year, what significance they're given, particularly in the European tradition, if there's anything specifically about the spring equinox.
Well, certainly the events of Christmas, of the conception of Christ, and of the birth of John the Baptist and the conception of John the Baptist, that's around the four interesting points of the year. But and that partly came from ancient theory as well, that that these dates had to be perfect, or also the birth of Jesus came from the concept that he must have died on the same date that he was conceived, and that's where the time for Easter comes from as well.
Yeah.
So there's interesting things there. But I'm not sure I can comment too much on that again. It's slightly moving away from astronomy more towards computers, which was the theory of computing liturgical times, which is certainly a branch of science in itself, or some sort of science. Skill.
That's interesting. It's well, just talking about the events in Jesus's life. The very common tradition is that Imam Ali was born on Nowruz, on the spring equinox as well, and I think also other prophets were said to have been born on the spring equinox, or I think Abraham. I'd have to check, but yeah, there is this thing that these major religious figures ought properly to have been born on these astronomically significant days. Yeah,
very, very interesting. I'd love to read more about that.
I'll send you. I can send you a paper on Nowruz that's not too long, that I think you'd find interesting.
Michal writes about quite a number of Arabic astronomers. Kind of quite interesting, because there's a whole series, and I'm not quite sure who all of them are either, because they're Latinized in many cases.
Yes.
And that makes it very hard to follow who they might have actually been. But here you go. Here's one, for example, Jabir, Ibn al-Haytham, al-Zakali, all excellent astronomers.
Yes.
And many of them translators of Greek texts that are fundamental to the formation of astronomy after the 10th, 11th centuries.
Yeah, of course. Yeah, in the Islamic world, there were a lot of drivers of sort of astrological thinking, and also like practical astrology, because of the need to calculate all these calendrical times, the computing you were talking about, and directions to Mecca, and then just a lot of maritime, just exploration and that kind of stuff, which is happening.
I wouldn't call that astrology. I would say that is a part of astronomy, or then computing.
Sorry. Yes, sorry. I meant to applied astronomy, not astrology. Yes, sorry, I misspoke.
Okay.
Although astrology was helping as well, but I was speaking of the astronomical side. Yeah.
Okay.
In any case, those are my questions. Thank you so much. It was a shame that this excellent presentation didn't have a larger live audience, but it was my treat that I got to just jeopardize your time for I don't know how long, and get to
very late there, so.
every side thought I had you addressed. So thank you so much.
Yeah, and Brian, any questions from you, or is it time to go to bed?
I think there's no hard and fast time limit at all, but whenever you feel that you've kind of is there more that we want to go into? I am definitely far from an expert in these topics, but I'm very interested to learn about it, and maybe I'll definitely have to go over some of this, in order to really pick up on some of the things that are a bit over my head at the moment. But I really appreciate your presentation, and I think this is a very rich.
If you have any more questions, absolutely write down comments, and I can answer them in text, probably in more with some diagrams, which would be more helpful.
Yeah, and I look forward to going back to the Timaeus and rereading those little, those sections you had pointed out with a bit more of this context and understanding, and seeing what I might see now.
Cool. Well, thank you very much, everyone.
Thank you so much.
All right. Take care. And,
All right. Thanks, Brian. All right.
see you next time if you're off.
Yes. Yeah. God willing. Okay. Thank you.
Bye-bye then.
Bye.
All right. Good night.